Howdy folks, it's Mr. Ryan, and what we're going to do is we're going to look at a subject here in statistics. I'm assuming at this point that you probably have already learned how to use a z-table, how to calculate a z-score. You understand basically what a sample mean is and standard deviation. And what we did in the last video was we started to look theoretically at the idea of a population of sample means, okay? Now in this video, I'm going to try and focus most of my time on how to calculate or how to answer these kinds of questions, but I do need to do a little bit of theory here at the very beginning, okay? So here's what I want to talk about. What is the idea of a population of sample means? Well, probably up to this point, what you've been dealing with is you take a sample. That's a bunch of X values, a bunch of observations. Let's say you got about, 16 or 17 or 43 or 189 people or dogs or houses or trees or something like that. You have a whole bunch of these are all X's. They're all X values. They're different observations, different observations within the population. But you took a bunch of them, a group of them, and you took them from the population. And what you did was you added them all up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So here's 19 of them. You added up their values. Like this one might be a 43, and this one might be a 61, and this one might be a 52. You added up all these values, and then you divide by 19, and that gives you the arithmetic mean, or the average, okay? And in statistics, we call that the X bar. Okay, so you have this group of observations, a sample that you took from the population, and you have the mean. You also have the standard deviation of all those numbers. This is the sample standard deviation, and you have the sample mean. Okay, so and what you have done previously is you've taken one of those values, or maybe just a different value. And you might say, hey, what is the probability that that you'll grab from the whole population? Imagine this whole board is full of X's, okay? And these 19 X's are taken from that population. And you say, hey, what's the likelihood that I will arbitrarily grab an X value and it'll be less than 40? What's the probability that I'll grab an X value that's less than 40? And so what you would do is you would do a Z calculation. And you would do Z is equal to whatever that X value is, 40, minus the mean, X bar. So you would subtract away whatever this average is, whatever this mean is, and you would divide by the standard deviation of the population. This would give you a z-score. Hopefully you recognize this formula. Hopefully you have used it a good bit. And so you would find a z-score, which would be probably between about -3 and +3 maybe. And then you would look up on one of these z-tables, and you would find a p-value, a proportion, a population proportion. And then that would indicate. So let's say you get a p-value, and let's say that the p-value is like 0.0901, 0.0901. And then you would say, well, that's the proportion of all the x's that are less than 40. So that means that there's like a 0.0901 chance that you would arbitrarily grab any one observation and it would be less than 40. Okay? Well, now things are a little bit different. Okay, we're moving deeper into the statistics pool. We're getting a little more conceptual. We're no longer dealing with the individual observations. Here's what I need you to imagine. That we have this mean of all these observations, but now let's say that we have another sample. Let's say that we have a sample that includes a few of these and then a bunch of others that are not in that sample. A bunch of X's are all under here. That's another sample mean. And let's say that we have another sample mean over here with a bunch of X's, 19 observations, 19 more observations, right? And now let's say that, now here's what I need you to do. I need you to zoom out. Zoom out so that you can't see any of these x's anymore, and all you can see are the x bars. And when you zoom out, what you're going to see is a whole bunch of x bars. You're going to see a whole bunch of means. And underneath every one of these means, is a group of data, or a group of observations. Okay? Each one of these is a mean of 19 observations. This is assuming that our sample size is 19. And you've got, and so how many possible x bars can you have? Well, you can probably have like a Google or two Google or a Googleplex. It's a large number. Depending on how many are in the population and what your sample size is, you can use, and I mentioned this in the last video, you can use this combination formula, NCR, and let's say that there are, 5,000 in the population, NCR, and then your sample size is 19. If you do that calculation in a calculator, I mean, you probably get a pretty big number. See here, NCR, so we're going to do 5,000, PRB, NCR 19. That gives us, might say, oh, it's 1.5 times 10 to the 53rd power. What that means is that it's going to be 1.5 with 52 zeros after it. That's a big number, a really big number. It's about half of the zeros on its way to a Google. Okay? But that's a huge number. That's how many x bars there are. And what we have over that is the population mean, the mean of the entire population. It is actually the mean of all the sample means. Okay? And we call that the expected value of m. Now, it happens to also be equal to the mean of the population. If you were to add up, if you were to take the 5,000 units, all the 5,000 observations in that population, add them all up and then divide by 5,000, that is what we call that is the population mean, and it will be equal to the mean of all the sample means. Okay, I know we're getting real deep in the pool of in the statistics pool. All right, so here's what I'm going to tell you, though. So let's say n is 19. What we now have is, instead of having a bunch of x's under here, we have a bunch of x bars. So we will replace x with x bar. And we have replaced, what we used to have up here was x bar. So we had a x bar sample mean over a bunch of observations. But now we've replaced x bar, with mu, with the population mean. And then we used to have the standard deviation here, S. But now what we're going to have is, we're going to have the standard deviation of all of the sample means. Well, there's a special word for that, and I mentioned it in one of my last videos. The special name for the standard deviation of all the sample means is called the standard error. The standard error. And it looks like this. Here's sigma is the standard deviation of a population. It's the standard deviation of x bar. That's the sample means. Standard deviation of the sample means. So we do sigma sub x bar, and it's called the standard error. And so instead of having s here, we have sigma sub x bar. We have the standard error. So we are going to replace s with sigma sub x, with the standard error. And so now, Here's our formula. The reason I'm going through all this is so that you can understand the change I am about to make to our Z formula. We're going to have a new Z formula. It's basically the same thing, but we're going to replace X with X bar. We're going to replace X bar with mu, and we're going to replace S with standard error. S is going to get replaced with the standard error. And so our new Z formula that we're going to be using to answer these kinds of questions, you use it the same way to find a Z score. But the way you calculate it is with new kinds of variables. But it's still the same thing. Put a number here, subtract, divide by a number, right? Your Z formula, your new Z formula is now X bar minus mu over standard error. This is your new Z formula. And you're going to need to write this down, and we're going to use it to answer questions C, D, and E. Now the procedure is the same. Once you have a Z score, you then go into the standard normal distribution and you find a p-value, and then either keep the p-value if it's a less than, subtract the p-value from 1 if it's a greater than, or if you have two numbers, you have to find two p-values and subtract them from each other. So let's do that right now. But before we do C, D, and E, we've got to do questions A and B. Questions A and B want you to calculate the standard error. And there is a special formula for calculating the standard error, which I'm going to show you right now. Standard error. And you're just going to write it down and use it, okay? The standard error, sigma sub x bar, is equal to. You're going to take the population standard deviation, which basically in most cases has to be given to you. So like in this problem, it says a population of unknown shape has mu of 149. That's a population mean of 149. So we would be putting that 149 here where there's a mu. And it has a population standard deviation. That's a sigma, by the way. It's a terrible sigma. That's a little bit better, but not much better. Population standard deviation of 35.7. We're going to use this. We're not putting this number here because this doesn't say standard deviation of the population. It says standard deviation of the sample means. It says standard error. So we're not putting this number here. We're putting this here. The formula for standard error is the population standard deviation divided by the square root of n. N is the sample size. So these are the two formulas that you need to be able to answer these questions. So you better write them down and be ready to use them a lot. So let's look at this question. It says a population of unknown shape has a population mean of 149 and a population standard deviation of 35.7. And you're going to select a sample of n equals 115. So your sample size is 115. You're grabbing 115 items out of the population to measure and to accumulate their data. Okay? So now, part A says, what is sigma sub x bar, right? And this means standard error. What is the standard error? Well, here's the standard error. So in order to calculate the standard error, we are going to do the population standard deviation, which is 35.7. So we're going to do 35.7 divided by the square root of n. The square root of, and n is 115. So the square root of 115. And now we just have to get a calculator to calculate the standard error. So we're going to do 35.7 divided by the square root of, so I got to hit a couple buttons on here to get a square root. I got to hit second and then x squared. That gives me a little square root symbol of 115. And then I press enter and I get 33, excuse me, not 33, I get 3.329. 3.329. Okay, 3.329. And now we're done with that. We're done. That's it. What is the standard error? for a sample size of 115 with a standard deviation of 35.7, just 35.7 divided by the square root of 115 in the calculator, and we get 3.329. So that is our standard error with a sample size of 115. But look at part B. Part B says, what would the standard error be? What would it be if your sample size was 85? Well, if the sample size was 85, then the standard error would be 35.7 divided by the square root of 85. And this is going to be a different number because we're dividing by the square root of 85 instead. We're going to do it in the calculator. 35.7 divided by the square root of 85, and I get 3.872. 3.872. And so, my standard error for part A was 3.329, but now my standard error for part B is 3.872. And I want to show you that when the sample size went down, the standard error got larger. And that's an important quality. Something you should remember is smaller sample size leads to larger, sorry, let me write that down here. A smaller sample size leads to a larger standard error. Okay? Smaller sample size, larger standard error. Larger sample size, smaller standard error. And it's all because you're dividing by the square root of the sample size. So as this number gets larger, the overall quotient gets smaller. Okay? All right, let's move on now to part C. I'm going to move this formula, this z-score formula. Let's see, let's put the z-score formula up here. Our new z-score formula is x bar minus mu divided by standard error. Okay? Now, this question says, if you take a sample of 115, okay, so because we're going to do a sample of 115, that means we're going to use this standard error, the one that has 115 in it. So we're going to use 3.329 as the standard error. If you take a sample of n equals 115, what is the probability that your sample mean, your x bar, is going to be less than or equal to 143? To answer that question, we need a z-score. So your first step is to find a z-score. All right, so z is going to be equal to, let's go to our formula, x bar. Well, that's given in the problem. X bar, 143. X bar, 143. So I'm going to go 143 minus mu, the population mean, which is given in the problem, 149. Mu is 149. So 143 minus 149 divided by the standard error. And the standard error for 115 is 3.329. So 3.329, we're just going to do this in the calculator. So we're going to go 143 minus 149 divided by, that's negative 6, divided by 3.329 gives us negative 1.80. Negative 1.80. Now we have a z-score, and we know what to do with a z-score because we've done this a lot. We go to our z-table and we find negative 1.80 and find the p-value. Negative 1.80 is 0.0359. Gives us a p-value of 0.0359, right? Now, if it's a less than question, this is our answer. If it's a greater than question, we're going to do 1 minus this number. And if it's a between question, then we need 2 z-scores. But this, look at this. This says less than or equal to 143. It's a less than question. So that means we're going to use the p-value that we found because all the values in this table are all less than p-values. So our answer is the probability of getting a sample mean less than 143 is 0.0359. Let me explain what this means. Let me explain what you just determined. You take a sample, 115 people, or dogs, or houses, or trees, or doors, or walls, or chairs, pieces of candy, and you're going to find out what the mean of those observations are. And what it's asking is, what is the likelihood that that mean for those 115? What is the likelihood that the mean is going to come up as less than 143? And the probability is 0.0359. That means like 3.6%. There's like a 3.6% chance that the mean is going to be less than 143. And that's not a very good chance, right? 3.6%. Okay? So there's kind of a low probability that you're going to get a mean from this sample that's smaller than 143. Okay? All right, let's try this next one. This next one says if you take a sample of 85, now your sample is 85. Because your sample is 85, you're now going to use the standard error for a sample size of 85, and that standard error is 3.872. So we're going to do all the same calculations, but we're going to use different numbers. We're going to use a standard error of 3.872. We're still going to use a mu of 149, but the question says, what is the probability that your x bar, that your mean is going to be greater than? What's the probability that your mean is going to, sample mean is going to be greater than 145.7? Okay, well, we need a z-score for that. So z is going to be equal to, well, what's the x bar? Well, they gave us an x bar of 145.7. So 145.7 minus the mu, the population mean, minus the population mean, which is 149. Minus 149 divided by the standard error. And the standard error for a sample size of 85 is 3.872. 872. And we're going to do this in a calculator, right? So we're going to go 145.7 minus 149, enter, that's negative 3.3, divided by 3.872 gives us a z-score of negative 0.85. And so now we're going to take that negative 0.85, and we're going to go into the z-score table here, and we're going to find negative 0.85, which gives us 0.1977. So this leads to a p-value of 0.1977. Now, this question is asking greater than. What is the likelihood that the sample mean is greater than 145.7? Well, this is the probability that the sample mean is less than 145.7. So we have to do 1 minus 0.1977, which will give us 0.8023. So the answer to this question is P equals 0.8023. So that's actually a really good chance. That's like 80%. It's like an 80% chance that when you take a sample of 85, that the mean that you get, the sample mean, is larger than 145.7. Okay? All right, let's do one more question, and I think you'll have the gist of how to do these problems. Maybe, you know what we'll do? After we do this question, we'll do one more. I'll change up the numbers, and we'll answer all these questions one more time using these formulas, just so that you can feel comfortable and know what you're doing. All right, so this last one says, if you take a sample of n equals 115, that means that we're going to use the standard error from the sample size of 115. We're going to use 3.329, right, down here. It says, what is the probability that your sample mean from that sample? What's the probability that you're going to draw a sample of 115 units, and it's going to have a sample mean that's between 149.9 and 156.6. Well, this is a between question, so we need two z-scores, right? So let's set up our two calculations for two z-scores. The first z-score is going to be for 149.9. So we're going to do z equals x bar 149.9, x bar 149.9, minus mu, the population standard deviation, or not, excuse me, the population mean, which is 149, so 149.9 minus 149, divided by the standard error, and we need the standard error from a sample size of 115, so that's 3.329. 3.329. And we need a second z-score. The second z-score is for a mean of 156.6, a sample mean of 156.6, minus mu, the population mean, which is 149, divided by the standard error again, which is 3.329. Same standard error on both of these. Now we're going to calculate two z-scores. So I've got 149.9 minus 149 divided by 3.329, and I get 0.27. 0.27. Down here we're going to do 156.6 divided by 149. Oops, minus 149, sorry. 156.6 minus 149 divided by 3.329 gives me 2.28. So I need a p-value for both of these. So I'm going to go into the z-score table, and I'm going to look up both of these z-scores. I've got 0.27, which gives me 0.6064, and then 2.28, which gives me 0.9887. So I've got two p-values, and now, since it's a between question, I'm going to subtract the smaller p-value from the larger p-value. So larger, 0.9887, minus smaller, 0.6064. So 0.9887 minus 0.6064, and I get 0.3823, and that's my answer. So my p-value, my answer here, p is equal to 0.3823, which means there's about a 38% chance that this sample, that when I take this sample, that the sample mean, x bar, is going to be between 149.9 and 156.6. Okay? So we answered all those questions. So you have to be able to calculate the standard error for whatever the different sample sizes are. You have to be able to calculate the probability that a sample mean will be less than, the probability that a sample mean will be greater than a number, and the probability that a sample mean will be between two numbers. Let's try one more example. All right, folks, here's another situation. We've got a population of unknown shape that has a population mean of 85 and a population standard deviation of 18.7. You're going to select a sample of 103 units. The first question says, what is the standard error? Well, we're going to use our standard error formula here. Standard error, oops, that's not a very good sigma. Sigma sub x bar. Okay, so our standard error is going to be equal to the population standard deviation, which is 18.7, divided by the square root of the sample size, the square root of 103. So we need a calculator to be able to do this. All right, let's grab a calculator, and we're going to do 18.7 divided by the square root of 103. And we get 1.84. 1.843. 1.843. That's rounded. It's actually 1.84256, but I rounded this up to 3. Okay? Now it says, well, what would the standard error be if your sample size was 54? Okay, well then our standard error would be equal to population standard deviation, which is 18.7, divided by the square root of the sample size. In this case, the sample size is 54. Square root of 54 equals 18.7 divided by the square root of 54. Now remember what we said. The smaller the sample size, the larger the standard error. So this should be a larger number than this, right? Okay, and it is 2.545. 2.545. Okay, so that's a much larger standard error than this one right here. Okay. Okay, so now let's go to part C here. This says if you take a sample of 54, that means we're going to use the standard error that goes with 54. We're going to use 2.545. If you take a sample of 54, what is the probability that your sample mean will be less than 81.6? Well, we need a z-score. If we're looking for a probability, we need a p-value. To get a p-value from the normal distribution, we need a z-score. So we got to calculate a z-score. So z, here's our z-score formula. Z is equal to x bar from the question. Well, the sample mean that's being asked about is 81.6. 81.6 minus the population mean, which is 85. Divided by the standard error. We need the standard error at a sample size of 54, which is right here, 2.545. So, grab a calculator. 81.6 minus 85 equals negative 3.4 divided by 2.545, and I get negative 1.34. 34. Now I had to round that last one, but I rounded it negative 1.34. Now I need a p-value that goes with negative 1.34. So I'm going to go to the z-table, and I'm going to look up negative 1.34. Negative 1.3, 1, 2, 3, 4 is 0.0901. 0.0901. And this question is asking, what is the probability that the sample mean will be less than? That means, and all the probabilities in here are less than probabilities. So this answer is our answer. So the probability is p equals 0.0901. It's about a 9% chance, a 9% probability that, or 0.0901, that you're going to, when you take this sample here of 54 people, that your mean will be less than 81.6. Okay? All right, now let's try part D. It says if you take a sample of 103, so now we're going to use the standard error associated with a sample size of 103. So we're going to use 1.843 right here. Okay? All right, so we need a z-score. What's the likelihood, what's the probability that your sample mean is going to be greater than 92.2? So we need a z-score, which is going to be x bar. X bar is 92.2 minus the population mean, which is 85, divided by the standard error. Now the standard error for 103 is 1.843. So 1.843. Do that in the calculator. 92.2 minus 85. 7.2 divided by 1.843 gives us 3.91. 3.91. So we go onto the table, and there is no 3.9. The whole thing stops at 3.49. So what do we do? Okay, so here's what we do. When that happens, we go at 3.49, at a z-score of 3.49, that's a p-value of 0.9998. So what we're going to do is we're going to go up to 0.9999. That's what we're going to say. When you go beyond what's on the z-score table, you just go as high as you can. So we're going to say that the p-value is 0.9999. And because this is a greater than question, we have to subtract this from 1. And 1 minus 0.9999 is 0.0001. And actually what we would say is, we would say that the p-value is less than 0.0001. But if you say p is equal to 0.0001, that's fine too. Okay? And so that's our, that with a sample of 103, the probability, so this is a very low, it's highly unlikely that you're going to get a sample mean that's greater than 92.2. Very unlikely that that's going to happen. Okay? All right. Now, let's do this between question here. And it says, if you take a sample of 103, what is the probability that your sample mean is going to be between 80.7 and 82.5? So we need two z-scores here. We need a z-score that goes with 80.7. So we're going to do 80.7 minus the population mean, which is 85, divided by the standard error that goes with a sample size of 103. Well, that's up here, 103, 1.843. 43. And then we need a second z-score associated with 82.5. That's the upper end. 82.5 minus the population mean, which is 85, divided by the standard error that goes with 103, which is 1.843. We're going to calculate these in a calculator. So we're going to go 80.7 minus 85 gives us negative 4.3 divided by 1.843. And that gives us negative 2.33. Then we're going to do this one, 82.5 minus 85. That's going to give us negative 2.5 divided by 1.843. And that gives us negative 1.36. We need a p-value for each one of these. For negative 2.33 in the table, negative 2.33 is 0.0099. And the p-value for negative 1.36 is 0.0869. 0.0869. Now I know it doesn't look like it, but this is the larger p-value. So we got to do this p-value minus this p-value. 0.0869 minus 0.0099. Do that in the calculator. 0.0869 minus 0.0099. That gives us 0.077. 0.077. And if you wanted 4, you could put a 0 on the end here, 0770. But we'll just leave it as 0.077. And that means that our probability is 0.077. That's 7.7%. There is a 7.7% chance that when you take a sample of 103, that the sample mean will be between 80.7 and 82.5. This is what I expect you to do. I have a worksheet. Once you're able to do this, this will now take you to the next subject that we're going to do. We're just going to keep progressing and building our knowledge in statistics. But this is essential. You have to be able to identify the probability that a particular sample will have a sample mean equal to or less than or greater than a particular value. Okay? That's all I have for you. Good luck. Let me know if you have any questions.